I'm high up on the slopes of Mount Etna. This enormous active volcano is a splendid natural laboratory for studying all sorts of igneous processes. I'm going to start by looking at the form and structure of the volcano and at the variety of volcanic rocks that have been erupted here. And then we'll be using Etna as a kind of window through the crust and into the upper mantle beneath. The upper reaches of the volcano are built of very new ashes, volcanic bombs, and some lava flows. At first sight, the landscape is a bewildering chaos of dark, jumbled blocks of lava and gritty grey mounds of volcanic ash. This huge volcano has taken only about 100,000 years to form. That's a prodigious rate in geological terms. About a cubic kilometre every 100 years or so. The volcano's still very active, and it's still growing. There's an eruption of lavas and volcanic ashes and bombs nearly every year. These lavas come from beneath the Earth's crust. The uppermost parts of the mantle melt. Molten rock moves up through the crust, and a variety of lava types is erupted. Each eruption has its effect on the landscape of the mountain. The lavas have risen to the surface through an immensely complicated system of fissures and pipes, possibly connected to magma chambers. Some of the differences between the lavas may have been caused by cooling processes which occurred beneath the volcano. But before we can investigate these processes, we need to distinguish individual flows. Distinguishing individual flows will enable us to make a representative collection of the different lava types. This boundary marks the edge of the 1964 lava, which flowed over the top of the 1949 lava in the foreground. The surfaces of these young lavas rapidly become weathered and oxidized, and soon turn brown. This flow, like most of the lavas on Etna, is covered in rubbly, scoriaceous blocks, which were broken up by the movement of viscous molten lava beneath. Very occasionally, you can see evidence of more fluid lavas. This ropey pattern on the frozen surface of a lava channel is a sure sign of flows with lower viscosity. Individual lava flows are small compared to the whole volcano, which is about 750 cubic kilometers in volume and is built from tens of thousands of flows. Some of the lava flows can be up to 20 kilometers long. It's possible to pick out the lava flows of different ages by the amount and type of vegetation on them. The 20th century flows are dark. The lighter, browner flows were erupted in the 18th and 19th centuries and are colonized by simple plants like mosses, and especially lichens. As lavas flow down the volcano, they cut through the forested slopes.
forests have been established on lavas that are many hundreds, perhaps thousands of years old. Islands of these ancient forested lavas are often isolated by younger flows. The flat ground, covered in grass and bushes, is the top surface of a 16th century flow, and the dark rubbly flow on the left was erupted in 1780. These differences of surface texture and vegetation help geologists to map the different lava types. Inside, beneath the rubble, the flows look quite different.
The structure of the individual lava flows is pretty much the same all over Etna. They vary a bit in thickness. This one's just about average. But virtually all of them have got this rubbly base, a massive interior with vesicles, gas bubbles formed as the gases escape from the solidifying magma, and the rubbly top to each of the flows. This massive part is what's cooled on the inside of each of the flows.
This structure is formed at the front of the flow. The rubbly blocks on the top are continuously tumbling over the front of the advancing flow, and they become overridden, a bit like a caterpillar tread on a bulldozer.
Inside some of the thicker lavas on Mount Etna, you find these lava tubes. This one's quite small, but it extends back for at least 20 meters behind me before it curves away out of sight. These lava tubes carry the lava to the front of these thicker flows.
But lava is more commonly carried to the front of the flows in open channels, such as these in the 1787 flow. The lava channels curve and change direction as the flow fronts encounter obstacles in their path. This flow has been diverted round a cinder cone. Many of the lava flows have actually originated in cinder cones, which are scattered over the flanks of the volcano, some as much as 20 kilometers away from the summit. The cinder cones are not randomly scattered. Many of them lie on radial lines that point almost directly towards the summit of Mount Etna. No big volcano is just a simple tube direct from the upper mantle to the surface. The main eruptive focus may be the central summit, but a big part of the total volume of this volcano has been produced by eruptions from cinder cones, well down on the flanks. Some of them were probably connected to separate segments of the upper mantle with different compositions. This is the Valle del Bove, an enormous bite out of the eastern side of the volcano. Standing up from the floor of the valley, this volcanic plug represents a pipe which fed magmas to the surface. It's more than 10 kilometers from the main summit. Further from the summit, exposed in the steep valley walls, are great vertical sheets. These are igneous dikes, and they could well represent fissures that provided pathways for magmas which erupted on the surface. When the eruptions stopped, the magmas solidified in the fissures, and they now contain a variety of different lava types. These are some of the specimens that I've collected from several localities on the mountain. I've collected them from the massive, compact inner parts of lava flows. And these four will give you some idea of the variety of rock types that make up the lava that has built most of Mount Etna. Essentially, they're grey, fine-grained and crystalline. But the proportions of phenocryst minerals in them are very different. In this one, the phenocrysts are glassy greenish olivine. And in this rock, the phenocrysts are mostly black clinopyroxene. And this rock is crowded with big whitish plagioclase feldspar phenocrysts. And this one's rather different. It's very fine-grained, and you can only just see a few small white plagioclase feldspar phenocrysts. But altogether, these rocks represent a nice little progression of chemical composition. A progression in chemical composition from basic through to intermediate. These rocks will give you some idea of the variety of lava types that make up most of Mount Etna. But now, I want to look at the oldest flows of the volcano. So far, we've only examined the younger lavas on the upper reaches of Mount Etna. We have to travel right down to the base of the volcano to find the oldest lavas. This is Adrano. It's one of many towns which lie around the southern perimeter of the volcano. It's built on some of the oldest lavas of Etna. The eroded edge of the lavas forms this scarp, and their flat surface forms a large platform where they stick out from beneath the overlying younger lavas. The climate is warm, it's thickly vegetated here, and the local farmers take advantage of the rich volcanic soils which have been washed off the top of the ancient lava flows. These lavas represent the earliest phase of Etna's volcanic activity, possibly 100,000 years ago. There's a terrific contrast between these rocks and the younger lavas higher up on Mount Etna. These are much more massive. There's hardly any rubbly material between the flows, and so it's very difficult to see the boundaries between them. And at the base of this cliff, there's some very nice columnar jointing. So these were probably rather fluid lavas that spread out as extensive sheets across the countryside. And that was the first phase of the activity that built Mount Etna. Now, if we look at the rocks in detail on a fresh surface, they're grey, finely crystalline basalts. And they've got lots of olivine phenocrysts in them. Actually, they're not very different from the olivine-rich rocks we saw higher up on the mountain. But these great, massive flows are quite different from anything we've seen before. If we want to understand the relationships between all these different lava types properly, we have to look at them in much more detail, and that includes their chemistry. We can investigate the chemistry of the lavas and their phenocrysts in the Earth Sciences laboratories at the Open University. First, we want to establish whether the Etna lavas are related by fractional crystallization. But what is fractional crystallization? This is a thin section of an Etna basalt. Large crystals, phenocrysts, are surrounded by a fine-grained ground mass, which represents the frozen liquid. As the magma cools inside the volcano, crystals are formed which have a different composition from the magma. They separate from the magma because they're heavier. The column on the left represents the quantity of crystals that have separated. They leave behind a magma which has a composition different from the one we started with. Different portions of the same magma can cool under different conditions and separate different amounts of crystals. The magma which has the most crystals separated from it changes the most. In this way, a variety of magma compositions can be produced. To test whether this process has occurred in the Etna lavas, we need to analyze the lavas and their phenocrysts. This is an X-ray fluorescence spectrum of an Etna lava. The largest peak represents silicon. The other large peaks, aluminium, iron, and magnesium. But what about the composition of the phenocrysts within the lavas? These can be analyzed using the electron microprobe. A narrow beam of electrons is played onto individual crystals in the lava samples. The X-rays which are emitted are compared with X-rays emitted from standards of known chemical composition. The chemical variation of lavas can be shown by plotting one element against another. In practice, major elements are expressed as oxides. This plot of K2O against SiO2 clearly displays the variation in the Etna lavas. The upper group, with the higher potassium content, forms a linear trend. These are samples that were collected from the upper, younger reaches of the volcano. The lower group forms a cluster, and these are the older, massive flows at the base of the volcano. This is a thin section of one of the younger lavas. We can compare the composition of the phenocrysts with the composition of the lava by plotting calcium oxide against silica. Pyroxene plots in the top of this diagram, olivine in the bottom left. The lava itself plots near the middle. About half the phenocrysts are pyroxene and the other half are olivine. If an extract of phenocrysts in this proportion were removed from the lava when it was still a magma, the residual magma would change in composition, becoming richer in silica. The more phenocrysts that are removed, the greater the change of composition of the magma. This is the process of fractional crystallization. If it happens repeatedly as new crystals form, it will result in a whole series of liquids of different chemical composition. The Etna samples plot close to this line, and this suggests that they could have been produced by the fractional crystallization of parental magmas derived from the upper mantle. So we've shown that fractional crystallization could have produced the chemical variations seen in the younger lavas. But what about the older lavas? In the field, they look very different from the younger flows, more massive and with columnar jointing. And our analyses show that they have much lower potassium contents. The older and younger lavas form two separate series. Each group must have evolved by fractional crystallization from different parental magmas, which had different potassium contents. The simplest interpretation is that the older and younger lavas originated from different parts of the mantle which had different potassium contents. The ratio of two strontium isotopes, strontium-87 over strontium-86, enables us to investigate the chemical composition of the mantle beneath Mount Etna. The ratio of the two strontium isotopes is totally unaffected by the processes of melting and crystallization. Before the strontium isotope ratio is measured, it's first necessary to separate the strontium from the other elements. Rock powder is dissolved in concentrated acid, and the strontium is removed on an ion exchange column. The final strontium-rich solution is evaporated onto a filament. Inside the mass spectrometer, the filaments are heated up under high vacuum. Strontium ions are emitted and accelerated down the tube into a strong magnetic field where their path becomes curved, the different isotopes being separated according to their mass. The intensity of each isotope peak is recorded. The data from this mass spectrometer are processed by a computer. This is the mass spectrum of strontium isotopes in an Etna lava. The ratio of strontium-87 to strontium-86 is measured many times, and the mean of several hundred measurements gives the final result. We've analysed the isotope composition of about 30 lavas, and together they provide a fascinating new piece to this story. The younger volcanic rocks have similar strontium isotope ratios of around 0.7036, but those in the older rocks are significantly lower, about 0.7032. Strontium-87 is produced by the radioactive decay of rubidium-87. The size of the strontium-87-86 ratio depends mainly on the size of the rubidium-87 to strontium-86 ratio. Consider two portions of the mantle, which have different rubidium to strontium ratios. We'll assume that several 100 million years ago, they had the same strontium isotope ratio, 0.7025. As time passes, the decay of rubidium-87 changes the strontium-87 to 86 ratios. After a period of time, the two mantle segments have different strontium isotope ratios. The segment with the higher rubidium-strontium ratio now has the higher strontium isotope ratio. This kind of difference is typical of variations in the upper mantle. The older and younger lavas have different potassium contents and different strontium isotope ratios. This indicates that they were derived from different portions of the upper mantle which have different minor element and isotope compositions. The mantle beneath Etna is chemically heterogeneous. So Mount Etna is far from being just a jumble of lavas and ashes and cinder cones. It's got a definite structure. But more important, you've seen how the chemistry of volcanic rocks can tell us about the evolution of magmas and about chemical variations in the mantle deep beneath the crust.